So in this video, we're going to get some practice with trigonometric integrals. Basically, we're going to be looking at integrals where we have trig functions raised to powers. And the first thing you'll want to do is identify whether your powers are even or odd. And depending on that, you'll approach it in a different way, right? So for example, if you look at number one, we have sine to the third, and we also have cosine squared. And so at first, it's like, okay, well, we have one of each, an odd power, an even power. Focusing on the odd power first. And the idea is going to be to replace our sine cubed as a product of sine squared times sine. That sine to the first power that we're about to write. As a matter of fact, here, let's just go ahead and get started with it. If we go ahead and rewrite this, I've saved this sine x dx and back in order to be able to do a u sub. As you know, if we let u equal cosine, then when we find du, we're going to get negative sine x dx, and then we can do a u sub. So if we had the rest of this integrand all in terms of cosine, we'd be in good shape. And so what's going to happen with many of these problems is we're going to use some version of the Pythagorean identity, as you see up here, in order to replace sine with some form of cosine, right? Sine squared becomes 1 minus cosine squared from this, or do something similar with tan squared and secant squared, or cotan squared and cosecant squared. So let's go ahead and proceed with this one. I will just quickly say, as we move forward and we have trig functions only to even powers, then we're going to be looking at these guys. And then finally, it's sometimes helpful to use this when we have a product of sine to the first times cosine to the first power. So that said, let's continue with number one. So we are going to replace this right here with our Pythagorean identity in this fashion, like this. 1 minus cosine squared x. And now at this point, you could distribute in the cosine squared, but it's easier just to go ahead and let u equal cosine x at this point. So du is equal to negative sine x dx. And so we have our negative du is equal to sine x dx. And our integral becomes negative in front from our du. Our sine x dx way back there is going to become a du, right? Negative du. And then we've got our 1 minus cosine squared, which will look like this, times cosine squared, which is right there. And now we're in a pretty good situation for integrating. We'll go ahead and distribute. I wouldn't mind getting that negative taken care of, so I'm actually going to rewrite it as u to the fourth minus u squared du. I distributed in the negative and I switch the order. And now we can get antiderivatives pretty easily. 1/5 u to the fifth minus 1/3 u to the third plus c. Our last step, of course, is to bring back our cosine. So go ahead and pause the video, try number two. Notice the odd power of cosine this time, and proceed very similarly to what we did in number one. Let's go on to number three. So here you'll notice that we have a sine to a second power, right? We have an even power, and we're going to use one of the identities that we saw above, namely this one. This is called a power reduction formula, and it's going to give us an integrand where we have cosine to the first power, which we can integrate pretty easily. So rewriting this, the integral from 0 to pi over 2, we're going to replace sine squared of our angle with 1/2 times 1 minus cosine of 2 times our angle. And our angle in this case is 3x. So we have 2 times 3x dx. Bring the 1/2 out. And now we're ready to integrate. So we've got 1/2. Antiderivative of 1 gives us x. And from there, we'll get minus sine 6x. And of course, if I take the derivative of sine 6x, I'll get cosine 6x times 6 because of the chain rule. So I'm going to need a 1/6 in front, like that. And we evaluate. Sine of 6 pi over 2 is the same as sine of 3 pi, which is 0. So we just end up with 1/2 times pi over 2, which is pi over 4. So pause the video, go ahead and do number 4. Notice that you have cosine to the 4th power, that's an even power, which is the same as cosine squared, quantity squared. So you'll be able to use the power reduction formula for cosine and then square the result. Let's go on to number 5. Here you'll notice that we have even powers of both sine and cosine, and sometimes that might not be clear how to start off with it, but we'll just go ahead and start breaking it down and see what we can do with it. In other words, rewrite it in such a way so our exponents get smaller. So here we've got sine to the 4th. I'm going to rewrite it as sine squared x times another sine squared x cosine squared x dx. And at this point, I'm noticing I can use a power reduction formula right here, but this guy is really just sine x times cosine x quantity squared. In other words, I'm going to rewrite it this way. And the reason I'm rewriting it this way is I can use the identity sine x cosine x equals 1/2 sine of 2x. Right? This is actually a double angle formula for sine. If we multiply both sides by 2, you'll recognize that from when you took trig. But what that allows us to do is it allows us to rewrite this whole portion as sine 2x squared, and then we'll be able to use a power reduction formula there. So let's go ahead and rewrite our sine squared first as 1/2 1 minus the cosine of 2x. Again, that's the power reduction formula on this guy right here. And then rewrite our product of sine and cosine using this. Now we're here. So I'm going to factor out the half, and I'm also going to factor out this 1/4, right? Because it's a half squared. So we're going to get 1/8 on the outside, integral from 0 to pi over 4. We have 1 minus cosine 2x, like that. And then here we just have sine squared 2x, like this. So now let's go ahead and see what happens when we distribute our sine squared. We've got 1/8 times the integral from 0 to pi over 4. I'm going to get sine squared 2x when I multiply here. I'm going to put a dx there and then subtract off the integral from 0 to pi over 4, the integral that we get here, which is going to be sine squared 2x cosine 2x dx. And the nice thing about that is back here, we'll be able to do a u sub. And over here, we'll do another power reduction formula. And so we'll have 1/8, the integral from 0 to pi over 4. Here we get 1/2 1 minus cosine of 2 times the angle, which in this case gives us 4x dx like that. And then I'll put the 1/8 here. Integral. Now, let's go ahead and do our u sub off to the side. U is going to equal sine 2x. Du is equal to 2 cosine 2x dx. So we're going to get half a du is equal to cosine 2x dx. So I'm going to replace my cosine 2x dx with half du. So let's turn the 1/8 to 1/16. And then we've got our du and back. We're going to replace sine 2x with u, so that's being squared. And then if we change the limits of integration, plugging in 0 here for x, we have the sine of 0, which is 0, and plugging in pi over 4 in for x, that means we're getting the sine of pi over 2, which is 1. And there we go. We now have a nice integral and back, and we're able to integrate in the first integral as well. So I'm going to take the half out. We get 1/16. The antiderivative for 1 is just going to be x. Here we're going to get sine of 4x, right? The derivative of sine 4x is cosine 4x, but times 4. So I'm going to need a 1/4 here, like that. And that's being evaluated from 0 to pi over 4. Minus 1/16. We have 1/3 u to the third, evaluated from 0 to 1. So we have 1/16. We have our pi over 4 here. Plugging in pi over 4 right there, we're going to get the sine of 4 times pi over 4, which is sine of pi, which is 0. So that's going to just be minus 0. And then, of course, plugging in 0 for everything, we get another minus 0. So that's done. Minus 1/3 times 16 is 48. And we end up with 1 to the third minus 0 to the third. So when all's said and done here, we get pi over 64 minus 1/48. And we have it. We could make a common denominator and subtract. That's fine. Or leave it there. So go ahead and pause the video, do number 6. Number 7, we've got cosine squared and tan cubed. Let's go ahead and first rewrite our tangent in terms of sines and cosines. Of course, we can cancel. So we end up with sine cubed x in the numerator over just a single cosine x in the denominator. And one thing I'm noticing here is I've got that cosine in the denominator. It sure would be nice to let u equal cosine x. And then, of course, du would be negative sine x dx. And so we definitely have a sine x dx up there, but we have a sine squared as well, right? That sine cubed, you don't necessarily need to write this next step, but I'll just go ahead and write it just so it's really clear what I'm getting at here. We have this situation here, right? And because the sine x dx in back is going to give us a negative du, right? If we let u equal cosine x, it sure would be nice to rewrite our sine squared in terms of cosine. So we can use our Pythagorean identity and rewrite it this way: 1 minus cosine squared x over cosine x sine x dx. And then using this u substitution over here, we've got 1 minus u squared over u, and then sine x dx will give us a negative du. So I'm going to put du here and put the negative in front like that. At this point, we can rewrite this as 1 over u minus u du. I'm going to distribute the negative and switch the order. We get 1/2 u squared minus ln absolute u plus c. And then, of course, we're going to bring back our cosine to get 1/2 cosine squared x minus the ln of absolute cosine x plus c, like that. Go ahead and pause the video and do number 8. Number 9, we have secant to the 4th x. Let's go ahead and rewrite it as a secant squared x times another secant squared x. And the reason we like secant squared x is because we know it's the derivative of tangent, right? And so now if we go ahead and take that first secant squared and rewrite it using the Pythagorean identity involving secants and tangents, 1 plus tan x times secant squared x dx. Now we can see that if we let u equal tan x, du is going to be secant squared x dx. That gives us the integral of 1 plus u squared. The secant squared x dx becomes a du. Pretty straightforward integration here. And then finish it off by bringing back our tan x. Pause the video, do number 10. Number 11, we've got a tan cubed and we have a secant. So we don't have a secant squared this time. So letting u equal tangent isn't really going to work for us, right? But what we can do is we can rewrite this so that we have our tangent squared times a secant tangent like that. And now I'm hoping we recognize right there that that's the derivative of secant. So if I could just rewrite this in terms of secant and then do u substitution, we'd be in good shape. Well, it turns out we've got 1 plus tan squared x equals secant squared x. So that means that tan squared x is equal to secant squared x minus 1. So if we write this as secant squared x minus 1 times the secant of x tan x dx, we can let u equal secant x, and du is going to be secant x tan x, like that. And so now our integral becomes u squared minus 1 du, right? We replaced all that with our du, and here's our u squared minus 1. Integrating, we get 1/3 u to the 3rd minus u plus c. 1/3 secant cubed u minus, secant cubed x, I should say, minus secant x plus c. So notice that we had an odd exponent on tangent and we had a secant, kind of similar to example 12. Go ahead and pause the video, do 12. Number 13, we have cotan squared x. And in this case, we don't have a power reduction formula for cotan. We can do that for sine squared, we can do it for cosine squared, but we don't have it for cotan squared. So let's see what happens when we replace cotan squared x using our Pythagorean identity involving cotangent and cosecant. Well, cotan squared x is equal to cosecant squared x minus 1. So this integral becomes cosecant squared x minus 1. And the reason we like this is because we know how to get the antiderivative of cosecant squared. So we've got negative cotangent x, right? The derivative of cotan x is negative cosecant squared. So I think we're good there. Minus x. and that's evaluated from pi over 6 to pi over 2. So we're going to have, I'm going to go ahead and factor out the negative. I just don't want to make little careless errors. So I have cotangent of pi over 2 plus, because I factored out the negative, pi over 2 minus the cotangent of pi over 6 minus, not minus, plus, remember I factored out that negative, plus pi over 6. So cotangent of pi over 2 is 0, plus pi over 2 minus cotangent of pi over 6 is root 3 minus pi over 6. So we end up with a positive root 3, a negative pi over 2, and a positive pi over 6. And that should give us this. Go ahead and pause the video, do number 14. It's a little different from number 13. My hint for you is go ahead and split it up into the difference of 1 over secant squared minus tan squared over secant squared, and then simplify. And then you should be able to use some identities to get you to the solution. Number 15, here we've got cotangent squared and we have cosecant to the 4th. So we have even powers on both cotangent and cosecant. The first thing I'm kind of focusing in on is the fact that we know that it's nice to have a cosecant squared dy here, because the derivative of cotangent is negative cosecant squared. So if I could somehow change all of this to cotangent, I can do a u sub, and I'll be in pretty good shape. So we've got the integral of cotan squared y. Cosecant squared can be rewritten using our Pythagorean identity for cotangent cosecant like this. And now we can let u equal cotangent y. Du is equal to negative cosecant squared y dy. So negative du is equal to cosecant squared y dy. So that's going to give us negative integral. We're going to plug in our u for all of our cotangents, right? So we have u squared. We have 1 plus u squared. And the cosecant y dy in back becomes the negative du. So we're there. Let's go ahead and distribute the u squared. So we have antiderivatives that look like this. And then we'll bring back our cotangent. So now you're going to go ahead and do number 16. Number 16 is a little bit tricky. I'll give a little bit of a hint here. I'd be tempted to start off writing it as tan to the 4th x times tangent x dx, and then taking our tan to the 4th and rewriting it really as tan squared quantity squared. So like this. And then we can rewrite our tan squared as secant squared minus 1 quantity squared like that. That's using our Pythagorean identity involving secants and tangents. Then we can square out this quantity to get something that looks like this. Distribute the tangent, and you get 3 separate integrals. Now, with this one, you can rewrite it as the integral of secant cubed times secant tangent, and you're ready to do a u sub. With the second one, you're ready to do a u sub right now. Let u equal tangent, du is secant squared dx. And then finally, your integral of tangent, you might have this memorized, or you can go ahead and change it to sine over cosine and then do u sub. So that gets you most of the way there. There's number 16, and you can finish it up on your own.